We are going to start the first, the invited speaker of the Colloquium series in the spring 2015, Engineering 400. It's my pleasure to introduce Dr. David Kraft. Dr. David Kraft is a professor of mathematics and physics at the University of Bridgeport. He received a BS in physics at City College of New York and PhD in physics at Penn State University. At UB since 1982, he served as a graduate dean, School of Engineering and Science interim director, UB Research Corporation, and professor of... So you cannot hear me? Hello, can you hear me? Much better. Okay. So I'm going to start again. Dr. David Kraft is a professor of mathematics and physics at University of Bridgeport. He received a BS in physics at City College of New York and PhD in physics at Penn State University. At UB since 1982, he served as a graduate dean, School of Engineering and Science interim director, UB Research Corporation, and professor of electrical engineering. Prior to UB, he was professor of physics, the Cooper Union director, Manpower Division, American Institute of Physics, and the deputy secretary of American Physics Society. His research interests include nuclear fusion and astrophysics. Please join me to welcome Professor Dave Kraft.
Thank you, Professor Lee, and thank you for the invitation to address the engineering colloquium. The talk that I'm giving today is originally was a 3-hour effort which was presented in a class in the international school. The class was called Influential Minds. I will try to keep it down to 1 hour. There is a lot that I'm going to have to leave out, but if you find that I'm keeping you beyond the time that you expected to be here, please feel free to leave. I want to start by thanking individuals who assisted me, Dr. David Burton and Dr. Angela Santiago, who helped me with some of the images. I think you're all familiar with the news magazine called Time, and that at the end of each year it selects a person of the century, a person of the year. At the close of the 20th century, it decided to select the person of the century, and it selected Einstein. And the editors of Time gave their reason of why they selected Einstein rather than perhaps some other individual who might have been worthy, and we're going to go into that perhaps at the end of the talk. What I would like to do here is to review Einstein's scientific contributions, their continuing impact on science and technology, and his contributions to society. All of these were mentioned by the editors of Time magazine as the reason for their choice. So, here's the issue of Time magazine that came out at the close of the 20th century, where Einstein was selected as person of the century. So this talk is rather difficult to structure. Should I do it chronologically? Should I do it by topic, particular scientific topic that he addressed? Or some combination of what? It is the latter that I have decided upon. We'll be going chronologically for part of the time, then we'll focus on one of the scientific efforts, his scientific efforts, bring that forward into the present, and then go back in time to another scientific item, bring that forward, and in between talk about his life. So, he was born in 1879 in Ulm, Germany. He was named for his grandfather. This is following the German Jewish tradition of naming a child initials for a deceased relative. So it was a Jewish family, but not an observant one. His Jewishness will play a great role in his life, as we're going to see later on. Nonetheless, though, he was not religiously observant. He was fond of a sister who was born 2 years afterwards, and he was fascinated by a compass which someone gave him at about age 5. Einstein had a reputation as a musician, particularly a violinist, and he started his lessons early, and it's something he played his entire life, so on. He entered the Munich public school system in 1886, and in 1888, the Leopold Gymnasium. Now, you have to understand that word gymnasium is not our word gymnasium, right? It is what in Europe is called, say, what we call perhaps the upper years of high school and early years of college. It's called gymnasium. Now, he was slow to speak, and because of that, people thought he was dull, right? So, nonetheless, at age 7, his mother wrote, again, he is at the top of his class. Now, this is to dispel the myth that Einstein was a poor student. You find this all over the internet. They say Einstein couldn't do math. All this is nonsense, as I will show you. One thing, though, he liked to think for himself. He disliked rote instruction. He did not endear himself to his teachers. And his Greek teacher told him, let's say his teacher of Greek, not this Greek teacher, told him that you will never amount to anything. So anyway, he learned much from self-study. So in 1889, a medical student, Max Talmud, was offered with the family for a period of about 5 years. He met frequently with Einstein. He introduced Einstein to philosophical works such as Immanuel Kant's Critique of Pure Reason and to various other philosophical topics. He had a 1-year religious phase, but that was dispelled when he discovered mathematics. Someone gave him a geometry book, which he called his holy geometry book, and from there on, he did a lot of self-study. He learned mathematics on his own. He left the gymnasium without a diploma. He was asked to leave, and so on. He tried taking the entrance examination for the Swiss Federal Institute of Technology, that is known for short as the ETH. He failed it, but not because of scientific or mathematical shortcomings. Rather, he did not do well in languages or biology, so he went back to a gymnasium in Aarau, Switzerland, and in 1896 earned a diploma which entitled him to enroll at the ETH. In the meantime, he gave up his German citizenship. He disliked the culture of nationalism and militarism and said that he would rather be stateless rather than be a citizen of such a country. Here's his report card at the Gymnasium in Aarau. I computed his GPA on a score of 1 to 6, with 6 being perfect. He made 4.93 if you count all those courses as equally weighted, and so on. You notice that in mathematics, in algebra, and geometry, let's go back. Algebra and geometry, he got perfect scores. In physics, he got a perfect score, and so on. So anyway, you still find this on the internet, though, stories that he was poor in mathematics and a poor student, and I don't know why that persists. His early scientific influences certainly started with that magnet that someone gave him at age 5. His discussions with Max Talmud, as I mentioned, the geometry book. And in 1895, he embarked on the first of what are called in German Gedanken experiments, meaning thought experiments. He wondered what might it be like to ride along a light wave, right? Something, of course, that is not possible to do, but it fascinated him to think about it. Again, now we're in 1896 when he graduated from the gymnasium at Aarau. He commenced study at the ETH for a certificate that would enable him to teach in a high school, something. Fellow students there that he met were Marcel Grossman, who would play a part in some of his scientific work later on, and his first wife, Mileva Maric, so on. Einstein was not good at attending lectures, so on. He didn't take notes, and he studied from his friend Marcel Grossman's notes in order to pass examinations, and so on. He received a diploma in 1900, and applied for an assistantship at the ETH, but was rejected. So in the meantime, he asked for he applied for and received Swiss citizenship. He supported himself by tutoring and some temporary teaching in high school, and he applied for a position in the patent office in Bern. And here he is as a patent clerk. I'm going to set it over here so I can see the screen. He found there that he was able to complete his work quickly, and so in his spare time he started to do physics. So in 1901, he submitted his first paper to the Annalen der Physik, that means the Annals of Physics, that was the premier journal of physics in Germany at the time. The subject was intermolecular forces. He was awarded a doctorate in 1905. He's still working as a patent clerk. Now understand, he's completely outside any scientific establishment. Right? Working as a patent clerk does not enable you to make the acquaintance of important scientists. He's doing this all by himself or in the company of friends with whom he has scientific discussions. Now, 1905 was a signal year in Einstein's life. It's called the Annus Mirabilis, meaning the miracle year or something. As he describes it, a storm broke loose in my mind. What happened is that he published 5 papers in 7 months, all of them on different subjects, 4 of them as seminal papers for opening up new fields of study. There's a very good book on this subject, which was published 10 years ago on the anniversary of the 100th anniversary of 1905 by John Rigdon, called Einstein 1905, and I recommend it as good reading. What were those papers about? One, the particle nature of light in order to explain the photoelectric effect. The second one, on the measurement of molecular dimensions. That was the subject of his PhD dissertation. Third, the analysis of Brownian motion. 4, the special theory of relativity. And 5, mass energy equivalence. Says John Rigdon, the author, he says this creative outpouring stands alone in the history of physics. So let's go through, I'm going to go through 4 of these. We'll describe what it is he did, bring it forward in time to discuss what relevance it has, then go back to another one, and so on. We'll be doing this back and forth for quite a while. So, the Brownian motion paper. The significance of this, of his work here, was that it established the atomic nature of matter. You see, up to the beginning of the 20th century, the question of whether things like atoms would be believed in, that was rather murky. The subject goes back to antiquity. Lucretius wrote in the year 60, before the Common Era, observe what happens when sunbeams are admitted into a building and shed light on its shadowy places. You'll see a multitude of tiny particles mingling in a multitude of ways. Their dancing is an actual indication of underlying movements of matter. There are the atoms, right, that are hidden from our sight. A Brownian motion is observed if when you put a droplet of a liquid, let's say, or a colloidal suspension under a microscope, and you see lots of agitation of the liquid particles, and so on. And what Einstein did was he did a theoretical analysis of the motion and computed the probabilities for there being some average distance which they travel in between making collisions and so on. And this was confirmed in experiments by Jean Perrin some years later. Perrin's work received the Nobel Prize for him. And it is generally credited to Einstein that he established the atomic nature of matter as fact rather than speculation. Bringing it forward to current times, the application of Brownian motion lies simply in its being a model for processes in diverse fields. I've listed just a few of them. So you see fractal, medical imaging, robotics, astrophysics, stock market analysis. There's a very good paper I read a while ago called On Brownian Motion in the Stock Market. Manufacturing, decision analysis, etc. One can go on. You can find lots of examples on the web. Let's go to another paper, the photoelectric effect paper. Now, we have to talk first about the nature of light. What was known about light? What had been known? Isaac Newton, early in the 18th century, composed a particle picture of light to explain the phenomenon of reflection. Right. Later, Huygens, Young, Fresnel developed a wave nature of light because other phenomena that had been observed for light, such as diffraction, interference, polarization, and so on, could not be explained on a corpuscular or particle model. So wave nature was developed, and it was James Clerk Maxwell in 1862 who codified the laws in a set of equations which many of you will study called the Maxwell equations. And so, there he also united the phenomena of electricity and magnetism as being just two different aspects of some one single phenomenon. It was something that we'll have to say about a little bit later on. It also predicted the existence of electromagnetic waves. EM means electromagnetic, and which were later generated by Hertz in 1887. And the wave picture was successful in that it accounted for reflection, diffraction, interference, polarization, and so on. Hence, the corpuscular or particle picture of light was largely abandoned. However, we have an anomaly here, the so-called photoelectric effect. Now, I pictured that in the cartoon there. Here is a metal, and the circles represent the free electrons in a metal. The red wavy things are light beams. That's light striking the metal, and the blue arrows are connected to electrons which are liberated from the metal. That is the photoelectric effect. Now, what the wave theory could not do was explain certain phenomena that were observed with the photoelectric effect. Namely, that the, do I have the one? Is the laser on? Yeah. The maximum electron kinetic energy being proportional to the intensity of radiation that was not observed, yet the effect could not explain. The effect occurs at any frequency or wavelength, and that the first electrons were emitted in a time delay after the radiation struck the surface. Well, to see what Einstein's contribution was, we have to go back 5 years to the work of Max Planck, shown here. And he was interested to explain, or studying the energy that is emitted by so-called black bodies. And the effort was to try to explain how the energy emitted, the light energy emitted, varied with wavelength. Now, at that time, there were two separate theories. Let's go back. You see the blue curve there? There was one theory that could explain the left part of that blue curve. We're plotting their energy versus wavelength. The left part could be explained by one theory. The right-hand part, with that long tail, so it tails off to the right, could be explained by another theory. There was no one overarching theory that could explain the whole thing, right? Especially the curving over at the top and so on. And what Planck hypothesized was that the energy, the light energy, is emitted by so-called resonators in packets of energy. E is the energy of the resonator, that's the oscillating resonator that's emitting the light. And they said it's equal to the frequency. The equation says E equal h nu. Nu is the Greek letter which represents frequency of the light. H was a constant of proportionality, which is now known as Planck's constant, and is one of the fundamental constants of the universe. So, and with that hypothesis, he was able to generate curves, theoretical curves, that matched exactly what was observed. In other words, uniting the two different portions. Now, Einstein seized on this and said that said the following. He said, let's say that the kinetic energy, the maximum kinetic energy of the liberated electrons is given by the energy of the incident light, which he wrote then as the way Planck wrote it, h nu, and subtract from that an amount of the energy that's lost by the electron in its way from the interior of the metal to the surface. And with that explanation, with that model, that is explained then why the electron energy is dependent only on the frequency of the light, not on the intensity. That there's a cutoff frequency below which no electrons are admitted, and that the first electrons can be emitted almost instantaneously. Now, understand what the significance of Planck and Einstein's hypothesis were here. That light consists of particles of energy h nu. Actually, it was Einstein who said, Planck attributed the h nu to the sources of the light, whereas Einstein attributed the h nu to the light particles themselves. So now we have a particle picture of light needed to explain the anomaly introduced by the photoelectric effect. Right. Well, this was not easily believed, and a very famous American physicist, Robert Millikan, sought to disprove Einstein's hypothesis. What happened is that he ended up confirming it, and so on. What you see plotted here vertically is something proportional to the maximum kinetic energy of the ejected electrons, and horizontally the frequency. And the red dots are the experimental points. The blue line is the theoretical curve from Einstein's model, and you notice that the points fall bang on the theoretical curve. Millikan got a Nobel Prize for this, but notice the irony that he started out wanting to disprove it, and he ended up confirming it. These light particles were called quanta, but were later called photons, and they're called photons today. The photoelectric effect is something all of us are familiar with when we walk through a door that opens for us, right, without our having to push it, and so on. You find the effect present in various devices, such as those listed there, and so on. The subject of photonics derives from this concept, and applications today, of course, are widespread. Communications, manufacturing, and so on. Now, there was a further consequence to this hypothesis. Einstein established what we call the modern picture of the dual nature of light. Namely, you can observe it as a wave or as a particle, depending on the kind of experiment that's done. Now, this may seem strange to you, so let me give you a different example, one which is widely known, that supposing a group of blind people encounter an elephant, and you ask each one of them, what is an elephant? Well, the one who encountered the leg will say, an elephant is like a tree trunk. And the one who encountered the tail will say, no, an elephant is like a snake. And the one who encountered the ear might say that an elephant is like a pancake. Well, who is right? Answer, they're all right. What's the difference? They each did a different experiment. So the current picture of light is that it possesses a dual nature. It is a particle or it's a wave, depending on what kind of an experiment is done on it. Now, this duality inspired the Frenchman Louis de Broglie in 1924 to establish another hypothesis. He reasoned as follows: just as light has both particle and wave properties, so perhaps matter, which certainly by definition has particle properties, that matter might also have wave properties. This is called the de Broglie hypothesis, and the waves that are associated with matter were called matter waves. This was confirmed very quickly a few years later in the experiments of Davis and Germer at the former Bell Telephone Laboratories. And what this gave rise to was the field first called wave mechanics, now called quantum mechanics. Quantum mechanics has been one of the most successful physical theories enabling to explain a phenomenon on a microscopic scale where classical physics cannot be applied. So, I do not expect you to be able to read this slide. I simply want you to look at the lines. The names on the slide are the people who contributed to the development of quantum mechanics and of the quantum theory. Whoops, let's go back. Einstein is right there. Notice that there are more lines either emanating from or converging on Einstein than on any other person. These are the people who contributed to in the early stages of the development of quantum theory. Einstein received a Nobel Prize, the Nobel Prize for Physics for 1921, actually in 1922, because they didn't award any prize in 1921. What did they award it for? Well, it says, for his services to theoretical physics, which we haven't looked at yet very much, except for one thing, and especially for the discovery of the law of the photoelectric effect. Now, I think you all know there's a lot coming, a lot of other work that he did, and you wonder, why did he not get the Nobel Prize for that? We can discuss that later. But at this point, the photoelectric effect and the hypothesis, the particle hypothesis of light had been well established, and so they felt safe in awarding the Nobel Prize for that. The first of two papers on relativity were published in that 1905 period, and the first one called On the Electrodynamics of Moving Bodies. Now, before Einstein, here is what was believed. Suppose we have here a train moving at a constant speed in a straight line. Those of you that study physics know that's called uniform motion, right? And there's an observer on the train, and we're going to call him S prime. There's also an observer on the station platform, and we're going to call her S. Now, S, the person on the platform, says, I'm at rest, the train is moving. S prime, the observer on the train, says, I am at rest, the platform is moving, right? What happens? These are observations made in different frames of reference. And unless one of those frames is accelerated, meaning a change in velocity, there's no experiment that can tell which frame is at rest and which one is in motion. Right? We say that neither frame is, quote, privileged. Yeah. And the laws of physics are expected to be invariant, meaning the same, in both frames of reference. Now, suppose the train is moving at 100 kilometers per hour, as measured by the observer on the platform. Right? The fellow on the train, S prime, he rolls a ball on the floor of the train in the forward direction, and he measures it going at a speed of 2 kilometers per hour away from him. In other words, 2 kilometers per hour with respect to the train. The person on the platform will see that ball moving at what speed? The speed of the train, 100 kilometers per hour, plus the speed of the ball relative to the train. That person on the platform will say that ball is moving at 102 kilometers per hour. Right? This is classical Galilean, so-called Galilean relativity at work. Now let's change the picture. Instead of rolling a ball, the fellow on the train has a flashlight and he shines the beam in the forward direction. Right? He's going to measure the light speed. Now I think you all know that light speed is usually designated by the symbol lowercase c. Right? So he measures it at c kilometers per hour. According to Galilean relativity, the observer on the platform should measure that light speed at what? C plus 100. But that's not what happened. The one on the platform also measures the speed exactly as c. Right? This is we're talking now about observational effects. So, point is, the Galilean relativity cannot account for this. Now, in 19th century, physicists postulated that S prime is in a so-called preferred frame of reference in which the light speed is c, and other frames in relative motion to which you observe the speed according to Galilean relativity. A preferred frame is one, as I say here, which is at rest with respect to the medium in which the light propagates at speed c. Now, you know that it was believed that all waves require a medium in which to propagate. In other words, you would not hear my voice right now if we were in a vacuum. Right? The fact that we are not in a vacuum means that there is some medium in the room which can propagate the sounds which I emit. So, since waves require a medium, an ether was postulated as being the one with respect to which the preferred frame is at rest. Well, the latter part of the 19th century, in the latter part of the 19th century, there was much effort consumed in attempting to detect the ether, especially the motion of the Earth through the ether, and all attempts failed. So, what we need is we need another theory that does not involve an ether. And now along comes Einstein in 1905. And he announces two postulates. One, the relativity principle, saying the laws of physics are the same in all non-accelerated frames of reference. We call those inertial frames. And a second postulate, that the light speed in free space has the same value, namely c, in all reference frames. So what happens as a result of this? No more ether. The first postulate forbids a preferred frame, and the second postulate forbids only a single frame in which the light speed is c. And so the Galileo and Newton ideas of absolute space and time were eliminated, both being relative to the observer. Well, what are the consequences of these? These are mathematical consequences, which one can derive quite readily. Essentially, instead of thinking of space and time as separately, you merge them and you speak of a space-time continuum, a four-dimensional space-time continuum. The equations, the Galilean equations which had described relativity, are replaced by equations which the theoretical physicist Heinrich Lorentz had derived for a different purpose some years earlier. The relativity of time was established, namely that simultaneity, for example, is not an absolute. What seems simultaneous to one observer will not seem simultaneous to another observer who is in relative motion to the first. The concept of time dilation, that your measurement of time is going to be different for different observers who are in relative motion with respect to each other. The relativity of length contraction. Let me describe that briefly. I'm holding an object here which looks to be about 8 or 9 inches long. I'm at rest with respect to this object. I make a measurement on the length. Now I walk at a constant speed, and you make a measurement on this thing as it's going by you. According to the theory of relativity, you're going to measure a different number. You're going to measure a smaller number than I, the person who was at rest with respect to this thing, measured. In other words, the rest length is always the longest length that is measured. Anybody who is in motion with respect to it will be measured. But now, for practical purposes, you would not see a difference because I'm not going very fast. You have to be going at light speeds comparable to the speed of light for these effects to be noticeable, to be measurable. But nonetheless, they exist at all speeds. Mass, a mathematical consequence of theory is that mass varies with velocity. A new velocity addition law has replaced the one that we saw earlier, that we saw failed. And we find that c is the limiting speed in the universe. Nothing can be accelerated faster than the speed of light. That does not mean that there cannot exist anything faster than light, that's going faster than light, but it has to be born going faster than light to begin with. You can't accelerate it through this value c and have it go faster. By the way, efforts have been made. Such particles are called tachyons. That derives from the Greek word meaning swift, tachys, which means swift one. And the attempts were made to detect tachyons several decades ago, and those were inconclusive. Anyway, it's a fun thing to think about. So, what's happened here? the time is the measurement of time is relative to the observer. Newton said time is absolute, true and mathematical time of itself and of its own nature, flows equitably without relation to anything external. According to Einstein, measurement of a time interval depends on the reference frame in which the measurement is made. So events which are simultaneous in one frame are in general not simultaneous in another. So simultaneity is not an absolute concept. Let's illustrate this by constructing a clock. Right? Now we have the same train here, and the fellow on the train, over on the left here, he has a device which emits a light pulse that travels upward, hits a mirror, and comes back down again. He measures the distance that it's traveled up, multiplies that by 2, because that would be the total distance, divides by what he knows is the velocity of light, c, and computes then a time interval. That would be the basic time interval associated with this type of clock. Instead of measuring the time for the swinging of a pendulum, you're going to measure the time it takes for a pulse to go up and back. Right? So he's got a number that's going to be twice the distance d divided by c. Now take the observer that's watching all this go, that's standing on the platform, watching all this as the train goes by. You have to imagine the train has transparent sides, and he can see this. What does he see? He sees the light pulse going up diagonally like this, and back down again there, right? And he computes this distance. They're both the same, these distances are both the same. Multiply it by, divide by 3 by c, and now what do you have? He measures a time interval, the time for the pulse round trip, to be greater than the time interval measured by the observer who was at rest with respect to the clock. Right? You see then that their notion of time, the notion of time intervals, depends on your state of motion relative to the clock. Moving along, some applications of STR means special theory of relativity. It informs all of modern physics. There are still people who don't believe it. They're these days considered to be cranks. You find them on the internet. It supersedes Newtonian physics, but it reduces mathematically to Newtonian physics in the limiting case of velocities being small compared to the velocity of light. So GPS timing corrections are another application. So there's a relatively new field called spintronics, which exploits relativistic effects as related to electrons and semiconductors, and this is being pursued because of it has promise for quantum computers and quantum communications. We're going to talk more about the effect that relativity had in other areas later on. So let's go on to the second paper on relativity. We're still go back in 1905 now. And does the inertia of a body depend on its energy content? Well, he says, Einstein, quoting Einstein, he said, the results of an electrodynamic investigation lead to a very interesting conclusion which shall be derived here. Derived means mathematically derived. Right? It showed that if a body radiates energy amount E, its mass decreases by E over c squared. Or saying it differently, the energy radiated is equal to the product of the mass lost times the square of the light speed. Or for short, E equal mc squared. Right? This establishes that there's a certain equivalence between mass and energy, and this equation has been described as perhaps the best known physics equation ever devised. If you ask anybody, do you know one physics equation, this is the one that they might know. Now, I have a clip here, and I'll have to ask Professor Lee exactly how we play this clip.
It follows from the special theory of relativity that mass and energy are quite different manifestations of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared in which energy is cut equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass will be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kokra and Gorton in 1932 experimentally.
Yeah. Okay. Good. So we can go back. If I click this, we'll go back. Here we go. This is not how theoretical physics is done. Right? Let's go. This is not how it's done. Right? It wasn't guessed at. It was derived. Now, what you just heard was Einstein explaining this. So I think we can all agree, without fear of contradiction, that Albert Einstein spoke at the engineering colloquium at the University of Bridgeport. Well, as Einstein said, if you caught it, the first experimental proof came in 1932. Remember, he discovered this in 1905. Of course, it was not believed. Right? And it wasn't until the technology became available to do the type of experiments that were now being done on subatomic particles, in nuclear physics. That was just being developed over those years.
Hold up, we can't hear you back here.
Okay.
Thank you.
You mean the whole lecture you haven't heard me? Would you like if I started over? Thank you, Professor Price. Okay, here we go. So this, what have been the applications of this? It's so crucial to the understanding of energies of elementary particle interactions, and explain the energy release in uranium fission experiments that were done by Otto Frisch and Lise Meitner in Germany in 1938. Now, this suddenly, the idea that fission, that you could have fission of uranium with energy release, led people to believe that something that we'll call an atom bomb could be constructed. And physicists were afraid that Germany, where this work was being done, might then have a lead in developing a bomb. This was just before World War II started. This was 1938. And so what happened was that emigre physicists, well, you have to understand, political conditions after the Nazis came to power in 1933 forced many Jewish scientists to leave their posts. Well, they were forced to leave their posts. In other words, they weren't allowed to hold their professorships anymore after the Nuremberg laws of 1935. And in other countries, such as Hungary, for example, they were fascist regimes. And so Jewish physicists emigrated to the United States and to Great Britain and other places in the West, so on. Anyway, some of them were in the United States. And two of them from Hungary, Leo Szilard and Eugen Wigner. Wigner eventually was a Nobel laureate. They were concerned about this, and they explained the problem to Einstein, saying that these experiments suggest that a bomb could be made. And they persuaded Einstein to sign a letter, which they composed, the letter addressed to President Franklin Roosevelt, informing him of this and urging him to start research in the United States to develop a weapon so that possibly to get it before Germany could get it, and so on. And this resulted several years, this was in 1939, this resulted several years later in the Manhattan Project. According to Einstein, whenever I write AE, I mean Albert Einstein, according to Einstein, he says, a chain reaction never occurred to me. So, here's Einstein with Szilard. And what are applications of this? Well, weaponry, as we know, right? First the atom bomb, now we have hydrogen bombs, fortunately not yet used. The nuclear fission means the splitting of heavy nuclei is the basis for current nuclear power systems. The fusion of nuclei, which means light nuclei getting together, right, is the basis, we hope, for future nuclear power systems. And it explains energy generation in stars. It's essentially then what provides us with what it takes to have life on Earth. Here's the most physics famous equation appearing in various places. It's in, whoops, let's go here. It's in the cloud here. It's spelled out on the carrier in Task Force 1, on the tower in Taipei, and on the Berlin Walk of Ideas, and so on. Back to John Rigdon, who wrote that book. He says, the year 1905 set a standard with wide-ranging influence. Of all human activities, thinking is a single activity that most clearly sets us apart from other life forms. Einstein's 1905 is an illustration of the thinking species at its best, the thinking person's standard of greatness. The title of his book is The Standard of Greatness. There were celebrations held in 2005. The American Physical Society declared it the World Year of Physics. They created the poster on the left. The poster on the right advertises a conference which I and several colleagues got together, a day-long conference which is attended by some 400 or so people summarizing Einstein's life and work and so on. It occurs to me that now in the year 2015 it's really time to get another one for reasons that I'll tell you about in just a moment. And that's the general theory of relativity. Referring to 1907, Einstein recalled having, quote, the happiest thought of my life. And he was thinking, again, a Duncan experiment, a thought experiment. If a person falls freely, he will not feel his own weight. Right? Again, and he says, it impelled me toward a theory of gravitation. Now, what came out of this was the general theory of relativity. And here's how it differs from what we've talked about so far, which is the special theory of relativity. The special theory of relativity was limited to reference frames that were not in accelerated motion with respect to each other and don't include gravitation. GTR, general theory of relativity, was completed in 1916, postulates the following. The laws of nature may be stated to have the same form for observers in any space-time frame of reference, accelerated or not. And secondly, in the neighborhood of any given point, a gravitational field is equivalent to an accelerated frame in which gravitational effects are absent. This became known as the principle of equivalence. Now, an example is this. Look at the picture on the left, case A. You have an observer in a box sitting in a uniform gravitational field. On the right, whoops, let's go back. On the right, case B, the observer is in a place where gravity is negligible, but he's being accelerated upward. And the principle of equivalence says that there's no experiment that you can do that would distinguish A from B. Right? That's the principle of equivalence. Well, what this suggests is the following, that a ray of light should be bent in a gravitational field. So here you see the fellow in the box doing an experiment with a flashlight, but as you can expect, the deflection would be so small as not to be measurable by any means that we could easily devise. So on. However, you have to look to laboratories on a larger scale in order to observe this. And I'll describe those in just a moment. But what the general theory of relativity then provided was a unified description of gravity as simply a geometric property of space and time. It generalizes both the special theory of relativity, SPR, and the Newton law of gravitation. In the limit of weak gravity, it reduces to the special theory of relativity, just as the special theory of relativity reduces to Galilean relativity in the limit of velocity small compared to the velocity of light. This is then how they are all related to each other. Now, some features and predictions. First of all, that there's going to be a time dilation effect due to gravitational effects. That there's going to be a gravitational time delay when light, for example, will pass near a massive body, meaning a large gravitational field, that there will be a time delay. And this was confirmed with sending radar to Venus and timing the echoes when they returned. It explained the precession of the Mercury perihelion and the bending of light by a large mass. Now I'll show those separately. We'll call these solar system tests of general relativity. In the left, you see a picture that's supposed to represent the orbit of Mercury. You know, you've learned that the planets travel in ellipses. The curves are ellipses. In the case of Mercury, it's not exactly ellipse. It's not a closed curve. It's one which precesses. And the amount that it moves from one cycle to the next is called the advance of the perihelion. Now, Newtonian physics, Newtonian theory of gravitation, was able to explain part of that shift. But the shift we're talking about is between the perihelion is the place where it's furthest from the sun. There's one to the next. Oh, it's symbolized here by an angle called theta. Newtonian physics was able to explain part of that. It took the general theory of relativity to be able to explain most of the rest of it. I think there's still a little small part that remains to be explained. The second thing, the bending of light. We'll have something to say about that in greater detail later, but briefly it's this. You have a massive body such as the sun, and you have a star over here. And the light from the star, that beam which just grazes the edge of the sun, is observed in a telescope here by an observer on Earth. Of course, that observer thinks the star is over there. That would be the apparent position. Right. Well, we're going to say something about that in greater detail a little bit later. Other implications